Okay, so I wanted to describe some ideas about topos theory, because I think this gives a rather good compression of the different results in the subject. Because there's lots of reasoning to do in topos theory, but I think that one can get by with just a few kind of ideas actually. Um, so the most important idea perhaps is this idea of sub B. So um, if B is an object in our topos, then there's this category sub B. Now the objects of sub B are the sub-objects of B, and we draw an arrow from one object to another when the first is contained in the second, in the sense that every arrow in the first sub-object is contained within the second sub-object. And the beautiful thing about sub B is that it's a Hating algebra, as I discuss in my video on my foundations video on logic and partially ordered sets. So it's a Hating algebra, and also I discuss this in intuitionistic logic and type theory. So the thing is that then the product of objects in this category corresponds to the AND or intersection operation. The coproduct corresponds to OR the union operation. Exponentiation corresponds to forming what basically corresponds to logical implication. Not, saying not A, corresponds to the exponential object of maps from A to 0. 0, the initial object, corresponds to false, and 1, the terminal object, corresponds to true. And that corresponds to the full sub-object. So basically, all the basic ideas in logic are here, apart from the other things that we're missing at existential and universal quantifiers. But we're going to get those a different way. Okay, so there's a clean way that those come about as well. So I think at the core of all of this is this sort of these adjoint functors. So in general, say we have a topos C, and or even I think it even works for a bicartesian closed category. Anyway, let's suppose it's a topos. That suits our goal. So then F is an arrow from A to B, and we have these, and so we can form F star. And what F star does is it sends an so let's draw it. So there's an arrow L from an object alpha to an object beta in C slice B. And then we have this arrow F from A to B. And then what we can do is just pull all this stuff back along F. So if we pull back alpha and we pull back beta, that's fine. We get new objects in C slice A, the pullback of alpha along F and the pullback of beta along F. So for example, for the pullback of alpha, we get something like this, and this will be our new arrow. So we get a pullback square like that. Let's pull back square, and we can do similar along Q, and then there'll be a unique arrow that completes this kind of triangular prism and makes the whole diagram commute. And that leads to the back square also being a pullback square, and that'll be the image of L under this pullback functor. So that's how the pullback functor works. And then the thing is, that's going to have a left adjoint that we call sigma F, and this is described in, I think it's described in McClarty's chapter on slice categories, if not on the fundamental theorem of topos theory. And similarly with the right, it has a right adjoint, which is pi F. And then the thing is that we can get this beautiful connection to do with slice categories, and we can investigate what it means for sub-objects. You see, this whole thing, well, it's very nice, is all this idea of slice categories. I mean, if we consider all this stuff, for example, in the case where b equals 1, then this arrow F in that case would have to be the unique arrow from A to the terminal object, and then all this stuff goes unique. And then if C is set, for example, then we can get some really nice connections with ideas of limits and co-limits. So there's all sorts of things we can do. And in general, this is just a really nice thing, because it also, in general, this gives us a way to convert between, so in general, especially in that case where b equals 1, that has interpretations in terms of dependent type theory as well, because it sort of has to do with looking at cases where we have extra variables, and when we're sort of thinking about our objects and arrows as having extra variables in B, for example, and doing substitutions and things like this. But anyway, another thing we can do, so the objects of C slice B are arrows into B. So if we just restrict our attention to the monomorphisms, then we can basically look at how all this stuff works on the full subcategory of C slice B, on the monomorphisms into B. And the interesting thing is that doing a pullback on a monomorphism gives a monomorphism. So then when we restrict things in this way, we can think of F star, well, basically the sort of restriction of it is this pullback functor that's pulling back monomorphisms into B into monomorphisms into A. It's this F to the -1 kind of thing. And in fact, it's going to be going from the lattice of subobjects of B to the lattice of subobjects of A. And so this is very pleasant. And so we're going to have that this is a pullback square. And really, we can just look at a restriction of what's going on. And even more lovely, and this is something I kind of guessed, but it just seems so, it seems like so rational that I kind of think it has to be true, is that the restriction of basically when we restrict F star to monics, it becomes like F to the -1, and then that has a left adjoint, which is this thing that gives existential quantifiers, and it has a right adjoint which gives universal quantifiers. Okay, so this is a pullback square. These are just inclusion functors. So when we take the above, I mean, let's just describe. There's going to the main thing I have to do, to follow through with this whole theory, is just work out the nature of these adjoint functors. They might even be written in McClarty. And a way to do it would just be to look at what happens with sets, and even in the case where B is 1, then it's surely possible, and then just generalize up. But yeah, I've got to understand the nature of these adjunctions. But anyway, like I say, we can restrict all this stuff to what's happening on monics, and then f to the minus 1 has left and right adjoints like this. And I think then that this kind of adjunction here is just going to be given by the restriction of this operating on the monics, and similarly restricting this to operate on the monics gives us our other adjunction, and these give us our existential and universal quantifiers. And so yeah, we're going to have that these are pullback squares, because the existential thing, I think, is just going to correspond to the restriction of the pi thing on the sub-objects. And similarly here, again, maybe this is even written in McLean somewhere, I've got to check. So in fact, just understanding pi f and sigma f is enough, I think. We can just think about how it restricts to monics. And then if we look at a special case of this, where A is x times y, and B is y, and f is p2, and say we're concerned with a formula psi, so we can think of the interpretation of psi over x and y as an arrow from x times y, capital X times capital Y to omega. Well then, this kind of extension over this existential quantifier exists x such that psi of xy. This is just going to be exist p2 operating on this extension of psi xy over x and y, and similarly operating exists of p2 on this extension gives this extension of forall. Okay, so doing forall p2 on this subobject of x times y gives this subobject of y, and that's the subobject for all x, psi of xy, extended over y. And yeah, in the case where y is 1, we get the restriction of this case to understand what just the pure formulas exists x such that psi or phi exists x such that phi and for all x phi. We can understand what they mean as pure formulas, in other words, as subobjects of 1, because subobjects of 1 correspond to arrows from 1 to omega, as in points of the truth value object. And those connect with limits and co-limits in the case of sets quite naturally. So yeah, that's it.